Hello, everyone, and welcome to our new chapter. We're going to learn about exponential functions and logarithmic functions this chapter. If you don't know what logarithms are yet, that's completely okay. You should have seen exponential functions in the past. We saw them in our finance unit, exponential growth. You've seen them in science class. We're going to see a warm-up problem very soon. We're going to learn how those apply to real-world situations. So today we're just going to start off by seeing some exponential functions, seeing the general equation form, and how to determine whether something's exponential growth and decay. So carbon-14 has a half-life of 5,730 years. This means that every 5,730 years, half of the sample will decay. So after every 5,730 years, we're left with half. So we start with 3,200 grams of carbon-14 in a sample. How much is left after 6 half-lives? So go ahead, pause the video, try it out. You might not need a formula, but how could I figure out how much is left after 6 half-lives? Okay, so let's see what you did. You take half of 3,200, and then you take half of that, and half of that, and half of that. I've seen students in the past do 3,200 divided by 2, and they get 1,600. And they divide that by 2, and get 800, and divide that by 2. Make sure you do it 6 times. Biggest mistake I see is students do 5 half-lives or 7 half-lives. They don't count that they do it 6 times. But ultimately, you're left with 50 grams of the substance. Now, this is carbon dating. This is really important. This is how we've determined the age of some fossils. And half-life is an example of exponential decay. So today, we're going to talk about exponential functions. We're going to learn that they have an initial value. They have a multiplier. There's going to be an asymptote. Growth is when we increase the rate. We start with an amount of something and then it goes up. Decay is when we start with an amount of something, it goes down. We're going to learn how to determine what is the function telling us. So let's use the questions for the warm-up, okay, to pull apart the pieces that are going to help us create the equation. So did the mass of the sample increase or decrease? How much carbon did you start with? What was your multiplier? And how do we write repeated multiplication? Because if I want to do 100 half-lives, I'd really like to just do something simple rather than repeat a multiplication 100 times. So pause the video. Try to answer these questions, because if you can answer these questions, you can write an exponential function. Okay, so we started with 3,200 and we went down and went down and went down. So the mass went down. We started with 3,200 grams. And here's the question I find very interesting. Your multiplier. You might say, well, I divided by 2. But what is dividing by 2? Same as multiplying by 1/2. So every time we took 3,200, we multiplied it by 1/2. We multiplied by 1/2 and multiplied it by 1/2. And repeated multiplication is exponents. So really what we did to get from the 3,200 to the 50 was we took 3,200 and we multiplied it by 1/2 and we did 6 half-lives. So we did it 6 times. That's an example of an exponential function. So if you can tell me certain pieces, what do we start with, what's our multiplier, we can write an exponential function. Now let's look at an example of exponential growth. So when I was younger, okay, I always wanted to have rabbits. I never got to have rabbits, and that's okay. But I thought it would be a good idea to have 5 rabbits. For some reason, I like the number 5. Now, not knowing what rabbits like to do, okay, I found out that if I had 5 rabbits, their population might start doubling and doubling and doubling, and then have a lot of rabbits at the end. So let's make a table. So if I start with 5 rabbits, how many rabbits do I have every year? And then how many rabbits do I have at the end of 7 years? So if you want to pause the video and make this table, great. If not, I will continue on momentarily and we'll see what this table looks like. So we're going to take a look at this table. Okay, at year 0, I start off with 5 rabbits. And then after a year, my population doubles. And then that population doubles. And that population doubles. And that population doubles. So I continuously multiply by 2 every time. I'm not adding the same amount of rabbits, I'm multiplying by 2. So it's constant multiplication. And after 7 years, I have 640 rabbits, assuming they didn't die or run away. Okay. And that's a whole lot of rabbits. But that's what exponential growth tells me. If I start out with a small amount and it doubles over and over and over again, I sooner or later get to a really big number. Now my equation is 5 times 2 to the x. And we're going to see what that looks like on a graph. But start thinking about, where did that 5 number come from? Where did the 2 number come from? We can put this equation together. So the graph looks like this. At year 0, I have 5 rabbits. At year 1, I have 10 rabbits. At year 2, I have 20 rabbits. This is the graph of an exponential function. I'd strongly recommend pausing the video, drawing this graph in your notebook. Make sure you have these 2 good points. Okay, down here there's going to be an asymptote. Which means that the curve is going to get really close to 0, but it's never actually going to touch 0. I can keep dividing by 2 all day long, and I'm never going to get to 0. So exponential functions are in this form. You could say y equals or f of x equals a times b to the x plus k, where k is your horizontal asymptote. A is your initial value and b is your multiplier. So in the rabbit population, we started with an initial value of 5, and our multiplier was double, so it was times 2. In the warm-up, we started with 3,200 grams, and our multiplier was 1/2. Now, depending on our multiplier, we either have exponential growth or we have exponential decay. So if the multiplier, if the b value is greater than 1, we increase. We have growth. You multiply something by a number bigger than 1, it gets bigger. And then the opposite's true. If you pick a number between 0 and 1, you have decay. So if our multiplier was 1/2 or 1/3 or 0.9, 0.6, it decays. And then our multiplier is never going to be negative because that doesn't really make any sense. That's a different family of functions. That's kind of a crazy family. So above 1, growth, between 0 and 1, decay. We need our initial value, our multiplier, and our horizontal asymptote, which will help us create an equation. So let's take a look at a few of these. I would recommend writing a bunch of these down in your notebook. These are examples of exponential functions. Which ones are growth? Which ones are decay? It may help to make 2 categories, put an exponential growth category and list the ones out of the 8 here that are in exponential growth. Same thing with the exponential decay category. Pause the video, take a minute, See if you can determine which ones are growth, which ones are decay. Okay, let's take a look to see how you did. So when the growth, okay, and I'm going to we'll go green for growth. Green might be risky. Let's go yellow for growth. Multiplier above 1, multiplier above 1, multiplier above 1. Those are growth. Then we'll use red, multiplier below 1, multiplier below 1, multiplier below 1. That's decay. And then these last two. Okay. If my multiplier is 1, it's really not changing at all. So that's actually, this is linear. Y equals 4 times 1 to the x really is just y equals 4. That's a horizontal line. So that's what we call a degenerate case, where you can write it like that, but that doesn't make any sense for exponential. And then the bottom case, y equals 0.5 times 0 to the x. 0 to the x is 0, times 0.5 is 0. And this is y equals 0, another horizontal line, also not exponential. So our multiplier can be above 1, it could be below 1. It's not going to be 1, and it's not going to be 0. If it's below 1, we have decay. If it's above 1, we have growth. So you can immediately tell, should the graph curve up or should it curve down? Are we growing or are we decaying? Now, I want you to try, make a graph. So pick a few x values, put them in, get some y values, get some points, and put them on a graph. We'll take a look at what these graphs look like. Okay, so let's take a look at some of the points. Okay, I picked 5 points. Don't know which ones you picked. I put in a 0 here. My starting value is 2. My multiplier is 4. So 0, 2, 1, 8, 232. If I want to go backwards, I divide by 4. Divide by 4, so I get 2/4, which is 1/2. Divide by 4 again, get 1/8. And I can plot some of these. Here I start at 3, and my multiplier is 1/2, or same thing as divide by 2. So 3, divide by 2, divide by 2. When I'm going down, I'm multiplying by 1/2. And to go backwards, I multiply by the reciprocal. Here, multiplied by 4. Go backwards, I multiply by the reciprocal. Now each graph, one graph would be growth. So we start at 2, multiplier is 4. We'd have a horizontal asymptote. Now you notice how terrible this looks if you don't do it on graph paper. I'm telling you, if you do it on graph paper, you're going to see that this looks like a nice, pretty curve. This one has decay. So exponential growth is the left function, exponential decay is the right function. Check it on Desmos if you'd like to see what it looks like on there too. Now, this looks very similar to compound interest, where we have a starting value, and if we have a rate problem, a percent problem, we can change these. We can change R to a decimal, and we can get a growth rate or a decay rate. Okay, similar to exponential functions, similar to compound interest, C is still our initial value, and R is our rate, which will generally be given to us as a percent. Could be given to us as a fraction as well. So let's take a look at a few examples. Car, $24,000 car depreciates at a rate of 10% a year. Write the model and tell me how much the car is worth in 5 years. And then Harry is going to buy stock that increases by 9%. Okay, write the model. and figure out how much he has after 8 years. So if you're feeling comfortable, try these out. Pause the video. If not, I will go through one of these, show you kind of how to do it, get you nice and comfortable. So if you're ready to move on, keep listening. If you need another minute, pause the video, try them out. So we'll deal with the first one. $24,000 car depreciates at a rate of 10% per year. Okay, I start with 24,000. My multiplier is 0.9. It loses 10%, so it keeps 90%. And then my equation is a times b to the x. And I'm going to use t here, and I'm going to use c for the cost, or the car will be worth. You can use any variable you want. So some of you are going to use y and x. I'm going to use the variables that tell me what I'm solving for. So that's the model. And now it says, find the cost after 5 years. So I put in 5 for t. And I put it in a calculator, 0.9 to the 5th times 24,000. And I get my car's worth $14,171.76. I can use this equation to find 5 years or 10 years or 20 years, however many years I want to keep this car. This is the model that works for everything. And then I could put my dependent variable in. Okay, same thing for the stock problem. I go up 9%, so I go to 109%, which is 1.09. I put 8 in for t, and I called it v here for value. Now, the only thing that this second question has that's different is it says, how much has he gained? So if I start with 300 and I go up to 597, I gain 297. So if you said he has 597, you're perfect, you're correct. But make sure you answer the question. Word problems are tricky like that. So here's another one for you guys to try. I strongly recommend you pause the video. Show yourself that you can do it. When you're ready, unpause. We'll take a look at it. You'll tell me your comfort level, and we'll move on. Okay, so let's take a look at these. Okay, increase, so plus 2.5%. Be careful changing the decimal. And then we want to find the population after 14 years. Create the model, then tell me how many are after 14 years. Same thing for this one, but this one has two parts. It's got an increase section. Then you can take that number, and after 15 years, what your house is worth. Then you can start new and say, after that, it loses 2%, so it goes to 98% for 10 years. So this one you got to break apart into two. So this was the challenge problem. If you got this, great job. If you got all the rest, that's awesome. Okay, that's exponential growth and decay. If the multiplier is above 1, it goes up. That's why I called it the up function. And if the multiplier is less than 1, it goes down. And we always have to know what we're starting with. And then we can put our exponent in depending on how many years or how many cycles we want to do this. So we'll continue to learn about exponential functions next time. We're going to work on more how to graph and how to come up with the equations if we're given other information.